Okay. So I want to finish up there's a sentence in the end. I have a bit of homework on for you. Okay. So this is just you're going to do a Fourier series of x squared going from minus L to L. You're going to graph it to Excel, stuff like that. Just so you can get some experience with it. Okay. So I want to finish up all the stuff with the Fourier series. Why we're actually doing it now when we're dealing with the spring, because it all ties in together. And then that will end basically one big section of the class. And then we're going to start kind of the whole main thing of what you really do with classical mechanics, which will be Lagrangians. And basically, we're not going to leave Lagrangians because once you get them, we're going to use the Lagrangian to basically hammer almost everything problem we're dealing. So that's, we'll have full stuff. Although I have definitely first. Okay, so that's it. I want to talk about two other series that we have related to this. And then I want to show you how everything's connected. So before you see how the Fourier series is connected to the Druid oscillator. And let's look at the Fourier sine and Fourier cosine series. Just so you know, if you take the advanced engineering math course, you're going to learn a lot of things like this. So there's going to be like a Fourier Bessel series, a Fourier Legendre series. You can put Fourier in a lot of contexts. And whatever comes afterwards here, it basically means that you're going to have some function, and you're going to represent this function as a linear combination of other functions. Usually, whatever comes after this is what you're using. So if you just say Fourier series, you normally take sines and cosines. But again, there's like a Fourier Bessel series, a Fourier Legendre series. There's a whole bunch of other functions you can put in there, all of which are really, really important. Am I still clear? I am still clear. Okay, so let's say we go back to our little function here. Here's our x. And here's our f of x. And let's say we have this. Now, suppose I want to look at a Fourier cosine series. So what is the Fourier cosine series of this guy right here, of x? So first of all, what do you know about a cosine series? A cosine series is, or cosines are, even. They're even. Okay, is this function even or odd? It's not. No. So what I'm going to do is I'm going to make this actually even. So what we're going to do is we will make f of x. And so what we do is that we have our function here. And we only look at this part of the function here. We completely blot out this f here. And now I have to make this even. So if I make this even, what would I have to then do? Yeah, this is, remember that even is f of x equals f of minus x. So I have to take this and basically flip it over here. So kind of the extension would be this up and down lines like this. So this part here, that's not how it even ends up, but you get the idea here. This is actually based on the flip of this function here. Then you look at the cosine extension of this. So then you'd have this guy here, and this guy like that, and this guy would then extend back over here like that. That's what you'd get. That'd be the Fourier cosine series. And if I write this f of x here, how do you think I'd write that? That'd be a naught plus so Fourier cosine series.
Some. Phase of n.
Yeah, the ANs always go to cosine y because they always go to cosine. It's going from n equals 1 to infinity of your cosine. It's n pi x over l. That makes sense. Okay, so without doing any work, what do you think the Fourier sine series is going to be?
Just making that odd.
And we're done. Okay, so the Fourier sine, the Fourier sine series is the odd extension. So how's that look?
F of x.
If it's odd. Have to go like this. Okay, and then make the odd extension. So this is L. This is minus L. So if I extend this, what would it look like? This can be this guy here. There, and then likewise. Okay. Now how would I write this one then? It would just be the b terms. The sum on n, 1 to infinity, bn sine x over l. That makes sense? So sometimes you hear about a Fourier sine series or Fourier cosine series. And it's the same idea, it's just your function is either going to be even or odd. Okay, that makes sense. Questions? I just want to say a little bit more about these things, like with the Fourier transform. What's it going to say a Fourier transform is?
Fourier is a continuous version.
Yeah, so the Fourier, again, we can think of this as being kx. And then what do? We basically integrate over all possible values of k. And then instead of writing it as a sine or a cosine, we write it as an exponential. There's a rule. Okay. What does the Fourier transform tell you? Something? So in other words, just one more thing. Let's see, Fourier series or Fourier transforms. Tell us. Tell us what? It's going to tell us basically how much of one particular wavelength actually contributes to something. Tells us how much one particular, let's say, one particular, I'll say, wave contributes to the signal. So what happens here? We said when we had let's do the Fourier transform. We said the Fourier transform is this guy here. And just a couple things here. Why don't you could say, well, why am I going from minus infinity to infinity here? So I'm having positive and negative k. What does that negative k mean? You say it doesn't mean a negative wavelength. It doesn't. Just to correspond to wavelength this way or this way. That's all it comes down to. And whether this is plus or minus here will vary from author to author. So some people, when they do this, you might see a minus sign here. Other people, when they do this, you'll see a plus sign here. That's going to vary from group to group. And also this factor of 2 pi. Sometimes that 2 pi won't be there. Sometimes it'll be the square root of 2 pi. Sometimes it'll be this 2 pi. So whenever you look at somebody's Fourier transform, don't be surprised if you're off by don't know factors of 2 pi. Because it depends on how things are setting it up. Again, my one professor in grad school, the only thing I had to learn from him, and it's helped out a lot. Most of that. Whenever you have a factor of dk, you make certain there's a factor of 2 pi. There, that's it. Now this, what you can do is you can also get the inverse transform. So this right here, this is actually, this guy here is going to be the Fourier transform. Right, the whole thing is the Fourier transform. I won't go like this. Actually, do this. I'll say the AKs here tell how much one particular e to the ikx contributes. So if I make a graph of something like this, it's the same thing with the when I had the Fourier series with the ANs and the BNs. Those coefficients are telling us how much one particular wave is actually contributing. So if I had to plot this AK here, I have something like this. Let's say I have that. What would that tell you here? That would tell you that basically right here, you're getting a really large contribution from these, from whatever the K value is here. As you're going further and further this way, these waves are contributing less and less and less. When you get over here, nothing's contributing. Likewise over here. Does that make sense? If I had something like this, if I plotted my A sub k like this, let's say I had this. Let's say you have that. What would you contribute? What would you realize? Only 3 are contributing. Which one's contributing most? The other one. This guy here. Okay, so that's what that thing is telling you. It's telling you how much of these different components are contributing. If you're an electrical engineer, this might be important because maybe what you do is you need to hone in on this dominant frequency here. Maybe you need to amplify it because maybe that's where your information is. Or maybe what it is maybe you have something like this and you need to basically kill this signal for who knows what reason. And so you might want to come up with a filter that then takes this component here and then eliminates it. So depending on what you do, doing with electronics, you do a lot of Fourier series, a lot of Fourier transforms. I would never challenge an electrical engineer in a Fourier transform competition. Mechanical engineer, I'd laugh at you. Materials engineer, I'll laugh at you. Okay, any other biophysics engineer, okay. Electrical engineer, I'm not going to challenge them in a Fourier transform competition. They might be unpopular. That's their bread and butter. They Fourier transform everything. My probably one of my best friends in grad school actually made a lot of mileage out of that. There's this, he was doing high temperature superconductors, and there's this awful expression. Then he tinkered with it and using the Fourier transforms and reduced this awful expression to almost nothing. And his advisor was really impressed. Entirely, because he had electrical engineering, so he was just really impressed with that. Okay. Yes.
So those two axes are the same, those two bad.
I just made this up. Okay, so this is, I just said, suppose we had this, what does this mean? Suppose we did this, what does this mean?
Okay.
I just made these up.
Yeah, because I know like there's like you convert from a time domain to
well, yeah, you can. So in other words, with a lot of the stuff that you do in spectroscopy. So what I'm doing here, I'm doing this in terms of x. You can also do this in terms of a time signal, and all you do is you go like this, and you go like here, and you go like this. Yeah, it's the same idea. Okay, so you can also do the time series as well. And often when you're doing spectroscopy, there's that one where you get the you have the Michelson interferometer, and you're doing the spectroscopy with it, and then you get that signal when you after you move the one mirror out. I think that's your
FTIR.
FTIR. And then what do? Then you Fourier transform that signal,
Okay.
and that Fourier transform signal is going to be this guy here, and then that's when you get all the information.
Okay. Thank you.
Oops, I should. I'll see this. Okay. Now, why do we worry about all this? This springs. It seems like it's disconnected. That's not. So, how our Fourier series? Connected to driven oscillators. So let's go back to our picture here. So here's our spring. This is M. Here's this guy here with that. We have a driving term here. That's our driving term. Whatever we've been taking this driving term to be.
Sine or
A sine or a cosine with same amplitude here. Well, suppose this driving term instead is I'll write this as a function of time, even though we have it as a function of x equal. But now let's say I have it like this. I have this I now have this generic driving term here. Let's say this is periodic, where f of t is periodic. Okay. How would I go about analyzing this? Well, if that f of t is periodic, I can represent that in terms of a sine Fourier, in terms of a Fourier series. I can say this f of t is going to be a naught plus a sum on n going from 1 to infinity of a n cosine n pi t over t. So I'm putting a time here, but it's the same idea. I'm going to sum on n going from 1 to infinity bn sine n pi t over t. Same idea. So what can I do? I can do the following. I can take my little problem here, and I can say if I set my problem here, I can put in my driving term here. I'm going to put in maybe here, and I'm going to say that this is going to be say that this is going to be cosine n pi pi t over t. Let's equate this to m dx like this. I'm going to put little ones on here. So I'm going to put a little 1 here, a little 1 here, a little 1 here. Okay. But what else could I do? I can have I'll put a little a on here too. I'll call this x1a, x1a, x1a. What else could I do? I could solve this, right? Because this is just this term here is just a simple driving term. What else could I do? Well, I could also do this one here. I could say this is minus k x2a minus b dx2a dt plus cosine 2 pi t over t equals m d2 x2a here. And I could do all the way down here. I could do my nth one. I could solve this. What else could I do? I could also do the same thing if I had a cosine, if I had a sine term. I also said that this is going to be minus k x1b minus b dx1b dt plus sine 1 pi t over t equals m d2 x1 of b dt like that. I could go all the way down to the another one here. I'll just put the nth one here. K x nb minus b dx n b dt. Am I so clear? Yes, I am. Plus sine n pi t over t equals m here and b here like that. Now what can I do with these? You can say, well, that's lucky. I'm glad we can solve all these because we know exactly how to solve them. I could take this term here. And what can I do? I can maybe multiply that by the A1 coefficient that I know what it is. I can take this expression here and multiply this whole thing here by the A2 coefficient. I could take this equation here and multiply this by the AN coefficient. I could take this one here, multiply it by the B1 coefficient. I could take this one here, multiply it by the N coefficient. Well, what would that give me? If I add, then I could take all of these and add them up. What would that give me? Right, let's look at this from here. So that I get what? I get minus k. I get A1, I get, and I also have to have an A0 term someplace there. I've got the A0 term. What would the A0 term be? The A0 term would not be a cosine, but rather 1. I should just having a 1 here. I forgot to put that in there. So I can have A0 minus k x0a minus b dx0a dt is 1 equals m dx0a that. So what would that give me? That would give me this term, 0a. Plus I would have a1 x1a all the way up here. Then I'll put in this guy here. Plus this b1 x1b. And then this b and xnb here. And have all those terms, right? But then I can do the same thing then for the first derivative term. I can pull out the minus b. I can pull out this derivative here like that. And what would this be? This would be the a0 x0a, this a1 x1a, whole thing here. Then I could add up all these terms here. And what would that give me? That would be then this a0 plus a1 cosine 1 pi t over t plus a2 cosine 2 pi t over t. I can then put in all those other terms here as well. And then what I'd have, this whole thing then would have to equal what? It'd have to equal m. I can then pull out my second derivative here. And this would be what? A0 x0a, this a1 x1a, this all those other terms here like that. And what would I have? What would I know about this whole mess here? That whole mess there as well. Oh, okay. I didn't put it. Yes, the way the data that I was supposed to include the sine series. What you said is correct. This is going to be the Fourier extension of that function here. This is really my f of t. And what do we have here? We have this function here is the same as this function here is the same as this function here. Okay. I will call this my x. What should I call it? I'll just call it x. Okay. So what I have here, I now have this actual solution to my problem. What I have here is I have minus here, which I now know what that is because I can solve for, I solve for those coefficients and I know all this. So I'm going to bring this guy here. Okay, and that's going to be my f of t here. And then this is my m here like this. Where this x is my a0, x0a, this a1, x1a, this da, 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 plus the b1, x1b, just look at that. This is, I know all those coefficients, so that right there is my solution. Pretty slick. Does that make sense? So we don't necessarily have to drive this by just something that's either a sine or a cosine. You can drive it as long as it's periodic by something weird, and we can still figure out the solution. Entirely because we can Fourier transform that signal. Does that make sense? Okay. I can't read people's faces this morning well. I can't really tell whether.
So when you like up there when you wrote A0, like
Yeah.
what's in front of the K? That's the same.
Yeah, so what I did, sadly I erased these all here. So I had all those, I had the solutions for the x0a, x1a, had all those here. Because we could solve those, because they just had a simple sine or cosine term for the driving term. I could solve those. So I multiplied the x0a term by a0. The equation that was x1a by a1. I multiplied all those individual solutions by those Fourier coefficients and added them all together. If I do that, all these terms here had a k, so I had a minus k, and this is all the what happens if you add up all the k terms and those expressions. Likewise, for the first derivative term, I can pull up all the member first derivatives, so I can pull that out. And this right here is acting on all these terms here as well, and then likewise here. So what happens is this whole thing here is identical to this whole thing here is identical to this whole thing here. So that gives me these terms. And all this mess here is nothing but my Fourier series of that original. So here's the function I wanted to solve. We know what the equation is. We know what the solution is. It's this right here. And I can solve each of these. I can solve for x0a. I can solve for x1a. I can solve for x1b. I know what each of those terms have to be. That makes sense?
Sense.
It's powerful technique.
So that X there is the solution.
For a general periodic driving force. And that periodic driving force need not be sine or cosine. It could be anything as long as it's periodic.
Okay, and the coefficients say how much of that.
How much of these, so in other words,
individual X.
how much of those individual frequencies
Yeah.
are contributing to that solution here?
So frequency, but like you wrote that as X.
Well, the x is the solution here, this x.
Okay.
Right? The frequency is coming in from the, because I Fourier transformed this guy. I'm sorry, I did the Fourier series term. So. Okay, cool. Yeah, this good? Make sense? And very powerful technique. Okay, so this is where test one is going to end. Material-wise, okay. I mean, we kind of already finished all over there. Now we're going to start new stuff here, and our next big gigantic topic is going to be Lagrangians. Okay, and so what we have to do is first I want to kind of give you where the problem occurs, and then I want to talk about the way we're going to proceed with everything. Because we're going to proceed using something which is actually is pretty pretty profound, it's fun, generalized limits. Okay, so let's talk about the problem. Let's ask, so here's the problem. Okay, we'll start with the question, why can't we simply use FNet equals MA on all problems? Yeah. I mean, F equals MA is perfectly fine, it's valid. Why can't I use that? Why do I want to just say, let's do something else? Here's why. When we actually do the formal derivation of this, which will be next week, I'm going to give you the adult version of the derivation. I'm going to use actually the derivation that I use in graduate school. It actually has all the bells and whistles in it. The reason why is that if you look at any of the other derivations that are usually done for undergraduates, I think they're stupid. Because okay, I'm a detail guy. My T's and my I's, my T's have to be across, my I's have to be dotted, or I stop. If I don't see where something's coming from, I can't go forward. Most of these other derivations just they in my opinion really fall short. So I want to show you what the actual derivation is. Okay, it'll be fine. Okay, but it is I'm not pulling punches on you. Assuming the whole adult derivation. Welcome to a very nice bonus. I'll be able to show you how you can extend this to E and M, these ideas. And that's normally not done in a course like this, but by doing it the way I'm going to, you're going to see we'll get a form that looks weird. That most people don't bother with. And you need that form if you want to put in E and M. And that's really important because if you want to then go to the quantum mechanical version of E and M, you need this for expression. And if you don't do that, it just appears stupid. Okay, so what are we gonna have? So let's try a problem here. So if I give you this problem here like this. Okay, let's say it's moving like this. I want you, now I say find it. Okay. What would you do?
Three body diagram.
Yes. What are all the forces on that little mass? Yeah.
The normal force.
No, what does normal mean?
Are perpendicular to.
Yeah, it means perpendicular to the surface. And there could or could not be friction on it. Doesn't. This we can have friction. And then what's the next step of any of these? You always set up you set up a coordinate system. Which way do you always take to be positive? We all the way take the direction of motion to be positive. Take this to be positive. You have this F net here. They break it up in components. Life is good, not a problem. Okay, here's what the problem comes in. Let's say instead we have this. So here's this. Okay, now I want you to find the acceleration of this. It's like easy peasy. You know, what's the free body diagram? Wait. Andy? No. The thing, fantastic. Looks exactly like this. We can even put friction on here if we want. No, great. What's the problem? What coordinate system do we use? For example, let's say my object is here. See, this is fine here, but if my object's over here, how's that normal look? My weight's still going down, that's great. This way it looks just like this way. Now the normal here is it's like that. Okay? If I'm over here, and this is mine. If I'm here, this is mine. If I'm here, this is mine. That normal is constantly changing directions. since that normal is constantly changing direction, I can't really set up one coordinate system to solve this. So the normal force is constantly changing. Our solution is going to be this. So what we're going to have to figure out how to do is we're going to have to figure out how we can take mechanics and remove the normal force. So that's what we want to figure out how to do. So we would like to. So the problem is N is constantly. Uh-oh, am I off the board? I am not. It's constantly changing. So we can't set up in a coordinate system to solve. I could say, well, wait, I could do this numerically. You know, numerically, I can actually go through and do this, and that's true. You could do it numerically. But when this is developed, computers don't exist. Okay, which is a good thing because basically developed grunge engineering, but have a lot of this stuff.
Numerically meaning you go through all the positions.
No, if I knew the actual functional form of this, then I could actually find what basically I could always come up with a normal for this. So then I could actually do F equals MA. I could actually just do F equals MA and break it up into just regular standard X1 coordinates. I could then figure out what any of these things are, and I can actually just solve them numerically. Okay. When this was developed, you couldn't do that. Not just that, but it's also just a good exercise to figure out how to get the normal force out of here. So the question is, how do we eliminate the normal? The other way, the way that this material is normally developed, this whole idea of the normal force is almost always omitted. And I think that's actually a major mistake because actually you really need the normal force to get the philosophy of why you're even developing this. Okay, so solution. Okay, we need to reformulate classical mechanics in such a fashion that the normal force is eliminated. I mean, the normal force is still there, but it's not going to appear in the formulation. Okay. So in order to do this, first of all, we need the idea of generalized coordinates. So before we do this, we need the idea of degrees of freedom and generalized coordinates. That's what they are. Okay, so the number of coordinates, number of independent coordinates needed to specify a problem is called the degrees of freedom. And that's going to be two. I'm going to just start saying D with degrees of freedom. Okay. The coordinates, the independent coordinates that are used to specify the problem are called the generalized coordinates. And we always use the symbol lowercase q for generalized coordinates. So q is used to specify generalized coordinates. So problems often have more than one Q. So as an example of this, you might have a Q1, a Q2, maybe up to Q7. Maybe there are going to be 7 generalized coordinates for the same. Okay, who knows? So I think the only way to really get an understanding of this is we're just going to start doing a whole bunch of examples and figure out what to do here. So let's take some examples here and then figure out what's going to happen. And we can understand what that word independent means. Because that's going to be the case. So let's take an example. Let's take one particle moving in 1D. Okay. So we have one particle. It's moving like this. Okay, how many coordinates do I need to specify that? Meaning, if I give you that coordinate, you can actually draw that picture. So how many coordinates would you need for this? One, just the x coordinate. But I have here, if here's my axis here like this, that, I would just come over here like this, I'd call this x like that. So the degrees of freedom is 1. I'll put the number here. Because I only need one coordinate here. In this case here, the q, I'll call this q here, I'll call this q1. This is just going to be x. Okay. So this system would just have 1 degree of freedom, 1. The generalized coordinate in this case would just be x. Fine. Let's take 2 independent particles moving in 2D. So how many coordinates would first of all, how many degrees of freedom would there be? Take this one here. So what would be the number of independent degrees of freedom I'd have for this guy here?
2.
Yeah, I can move in the x direction. I can also move in the y direction. So this would have 2, this would have 2, so you'd have the number of degrees of freedom for this whole thing would be 4. And you'd have 4 q's. In this case here, I could have what? You have this distance here. This would be x1, this is y1. This is, I'll extend it like this. This would be x2, this would be x2, and this would be y2 here like this. So the number of degrees of freedom is 4. And if I wanted the q's for this, I'd have it. What I call q1 or q2 or q3 doesn't matter. Okay, I could have q1 equals x1, q2 equals y1, q3 equaling x2, q4 equaling y2. Okay. Now, my friend looks at this and says, yeah, you're right, there are 4 degrees of freedom, but they're not the q's. If my friend is using polar coordinates. So we're going to all agree with this, That's not gonna change. Well, my friend says they're not the coordinates. Really, what I'm gonna have is that I'm gonna have this one R1. Then I'm gonna have a theta one. And then I'm gonna have this particle over here, so this is gonna be R2. And this will be theta 2. So my friend says, the generalized coordinates are really Q1 equals R1, Q2 equals theta 1, Q3 equals R2, and Q4 equals theta 2. Which one is correct? They both are. Now, this is going to show you one of the weird things about the Qs. What are the units for all these Qs here? This is another sort of the same. What are the units for all these Qs over here?
Different.
They're different. The Qs do not have to have the same units. Okay. Here I have a distance one, and here I have a radian. Okay, so your Qs do not have to have the same units. Okay, so let's get the same problem here. Two particles, but now they're connected by a rod, a fixed length. So let's take the exact same. Two particles connected by rod, fixed length L in two dimensions. So I've now this particle here, and this particle here. So here's my x1, here's my x2, and I know that this length here is L, and it's fixed. Okay. How many degrees of freedom do I have now? This one over here. Okay, I should call, I don't know why I could have concerned, let's call it position, but X is stupid. Sorry about that. So here's my X1, and here's my Y1. This is my X2, and here's my Y2. So it looks like we still have the same number of X's, but there's a very important word in the number of degrees of freedom and in the generalized coordinates. What do the Qs have to be? They have to be independent. Now, are these all independent? No. So let's figure out. So first of all, what do we know about this L? What would that L be given by?
In that picture.
Mhm.
X 2 squared.
Okay, upper level physical majors and engineers, but you know this coordinate, the L has to be
The difference between.
Side and side. Something.
and this is where if I had my white fluffy cap, the button would be pressed to the walls going in. Why stepped out?
Well, you just say it's x2 minus x1 squared plus y1 minus y2.
So exactly. Right, so you're out. Actually, well, it has to be the square root of x2 minus x1 squared plus y2 minus y1 squared. This is no. Right? Because this is fixed here. So what does it mean? How many of these are independent? Okay, I only need to have 3 of these would be independent. Right? Because if I know this one, and this one, because this L is fixed, I can know this one here. Okay, so in this case here, the number of degrees of freedom equals 3. And what could my Q's be? Q's could be x1, x2, I'll say y1, q3 equals x2, and then I wouldn't have a q4 because the y2 would be, it's not independent. what this means here, this value, this expression here. This is called a constraint. What we see here, the number of degrees of freedom. I'll stop it at this point. How can I write this? I could really take 4. So this would be my x1, y1, x2, y2. All those original coordinates. Then I have one constraint. This is the constraint. And this would be my 3. So what I'll try to convince you of on Monday, that what we're going to have is that this value here is really going to be the number of particles times 2 if we're in 2 dimensions. If we're in 3 dimensions, this is going to be, this is for 2D. If we're in 3 dimensions, we'd have an x1, a y1, a z1 for each particle. So we have 3 again for 2D. What I try to convince you of on Monday is that the number of degrees of freedom is going to be 3n minus however many constraints we have. So this would be for Monday. So the number of degrees of freedom going to equal 3n against the number of constraints. Okay. And then what we're going to have to figure out how to do is how to go about basically figuring out how to eliminate that normal force. And we're going to use a very, very subtle principle that's going to be referred to as D'Alembert's principle of virtual work. So I have to explain what the whole idea of virtual work is. I'm going to show you a picture. But as far as I can tell, my professor was the only one who ever drew this picture, which was the only time virtual work made sense. So you will learn. You'll be initiated into the secret society that actually will be able to, when somebody says, what's virtual work? You will be able to draw this one picture. As far as I can tell, it's the only picture I've ever seen anywhere that actually shows exactly what virtual work is. It was actually a very terrifying professor. It was actually a very tall man. Kind of looked a little bit like Kermit Munster. And he would just be quite intimidating. He was an excellent professor. He was teaching and he was going over this subtle idea. You know, this is very complicated the first time you see it. Does anyone have any questions? And he points to this one kid. You're always asking questions. Do you have any questions about this? That's how we did all this. Here's a friend. That's scared the hell out. But that's okay. Have a good weekend.